This has to be an exciting moment for you guys. This is our last lesson that's going to be on your final exam. And not to mention your chapter 8 test is the end of this week. And then next week is your final. So this is great to finish this up. 8.8, parametric. Again, another lesson that you at Med High are the first non-calculus BC students to ever have been taught this, at least in the last 15 years. So we're going to look at some basic concepts and talk about converting between parametric to rectangular. The last lesson we were doing polar to rectangular, rectangular to polar, and we had the option in our calculator to go to the mode and choose polar. Well, now we're going to be doing parametric. Now, parametric, metric is a measure. And so we're talking about looking at different representations of those measures of graphing. Parametric equation, he says it's a plane curve. That just means it can look just like any other curve you've done before on a plane with points x and y. But instead of graphing that point as an x comma y, we graph that point as possible two different functions giving the x and the y. In other words, the x value could be written as an f function with a different variable. The y component is also, wrong color and wrong marker. The y component will also be represented by a different function, and it also shares a variable t. So what you have is the x and the y and t are being your variables. The reason that parametric works, they're sharing the parameter t. So all x values are related to f of t, and all y values are related to g of t. Let's do your first problem. We're going to graph the plane curve defined parametrically. So let x equals to t squared. He's giving us what x is actually equal to. It's t squared. And y is 2t plus 3. Now you cannot graph parametric without having both equations. My t's are going from -3 to 3. So we make a table, and we'll start out with our t values. Then what we'll do is, since we know what t's are changing to, they will create different x's. They'll create different y's. So the t's he's using is -3, -2, -1, 0, 1, 2, and 3. So to get the x values, I'm going to do all the x's straight down because those are the easiest. Looks like all he's doing is taking the t and squaring it. 9, 4, 1, 0, 1, 4, 9. Now the y values are coming from taking 2 times the t and adding 3. So 2 times -3 is a -6. Add 3, -3. 2 times a -2 is a -4. Add 3, -1. 2 times a -1 is a -2. -2 added to 3 is 1. 2 times 0 is 0. Add 3 is 3. 2 times 1 is 2. Add 3 is 5. 2 times 2 is 4. Add 3 is 7. 2 times 3 is 6. Add 3 is 9. So now we plot these points. And we're graphing them. Well, let me just graph them with my x and y's. 9, negative 3. 9, negative 3. Let me do it black. Negative 3 and 9. That's down here. 4, negative 1. 4, negative 1. Negative 1, 1. Negative 1, 1. Oop, I messed up. Let's play 1, 1. It was 1, 1. Okay. 0, 3. 1, 5. 4, 7. 9, 9. Look at the pattern. We've got these points that go this way. Seems like a connects smooth curve. It's a plane curve. And that's a sideways parabola. You've done something like this before with... Okay, I'm going to go to a clean page so you can see what my slides are going to look like. I'm going to insert all my pictures and then I'll come back to you. Okay, I did go to mode. I turned it on to PAR. I typed in the two parametric equations, one for x and one for y. They come up together. You can't have just one, you need them both. That's the picture I saw because my window wasn't correct. So I'll show you what the window had. This was what just came up on my calculator. Here's where the problem occurred, was my T min was a 0 and my T max is a 1. Well, you know I went from negative 3 to 3 for T. So what I did was I changed the window. All I did was go to negative 3 to 3. I didn't change the T-step. I didn't change anything else. I just hit graph again. See, here's my mode key. That's where I went to get the parametric. And that looked pretty good. And I worked on the window a little bit and got the whole picture from negative 3 to 3. Because you can play with what your x's are going to be and what your y's are going to be. Go up here and look at that window, that screen again. Oh, not there. Maybe look at here. You got your x min, x max, y min, y max. So if I would have plugged in the correct numbers in beforehand, I knew I went as far over to, I went 9, 9. So I should have gone from at least 0 to 9, 0 to 9 for both. The min being 0, or the negative number doesn't bother it. It doesn't hurt it that you got some negative space there. But I cleaned it up here and made it look a little more went all the way to negative 9, went all the way to 9, went down to negative 9, and starting at 0. Actually, I went negative 3 or 4 or something like that to 9. Here's what the author had. There's the table, matches our table. And there's the graph. And it's obvious that when you look at the graph, the x's was x max was 9, and I think I put -9, but I didn't have to. It could have just gone to 3, -3. And the x's are 0 to 9. And the t's went from -3 to 3. So you get all that marked into your window. It'll graph just like that. Here's an example of all the different windows. This is a continuation. Scroll down. So not much different than my picture. Now let's see, example 2. Find a rectangular equation for the plane curve of example 1. Okay, so we already we had the graph. The graph was this sideways parabola, something like that, I don't know. So let's find the equation of it in rectangular, because we've seen them before. There are a lot of ways to do it. It doesn't, the easiest way, and he's going to want us to do it well, I'm just going to go take my x equation or my y equation, whichever is easier to use, and solve it for t. So I could take this equation and find out what t is, or I could take this equation. So in this problem, y minus 3 all divided by 2 is equal to t. So I take all of t and I plug it up into the x equation. So I get x now will be equal to all of y minus 3 over 2 squared. So notice the beauty of this equation. There's no t's left in it. I've eliminated the parameter t. So I'll FOIL that out. That's going to be equal to y minus 3 times y minus 3 divided by 4, because 2 times 2 is 4. That turns into x equals to y squared minus 6y plus 9. Each of these are divided by 4. So this is divided by 4, that's divided by 4, that's divided by 4. So x equals to y squared divided by 4 minus 3/2 y plus 9/4. That doesn't reduce. So that's an equation solved for x. Probably we didn't see it that way in our conics. We probably put the 4 with the x and wrote 4x equals to y minus 3 squared. That's how we wrote it in our parametric, if you recall, when we were doing the focal points and the stuff like that. But this is a perfect equation. That's a perfect equation. Chances are he gave us this one because that reminds us of conics. Remember the looking for the focal points and looking for the directrix and all that. And yeah, okay, there's that. Squaring, yeah, there it is. Beautiful job. Okay, example 3. We're going to graph another plane curve defined parametrically. So I'm going to remind you of an identity, since these parametric, the pair of those are trig. I'm going to remind you of this particular identity. Sine squared of anything plus cosine squared anything is always equal to 1. So if I take my x, solve this for sine, I get sine of t equals to x over 2. This one here, y over 3 equals cosine of t. So if sine squared t plus cosine squared t is 1, that would mean x over 2 squared plus y over 3 squared is equal to 1. Now that equation should look very familiar to you because that's x squared over 4 plus y squared over 9 equals to 1. Do you remember what that was? That was an ellipse. And if we're supposed to graph it, here it goes. I'm not even going to plot points. Remember, on the x, it's 4. So the square root of 4 is 2. 1, 2, 1, 2. I'm centered at 0, 0 because there's nothing being added to the x or the y. The y, 1, 2, 3, 1, 2, 3, because the square root of 9 is 3. So, yeah, I kind of exaggerate. I should make my tick marks better on my be a little more proportional. 1, 2, 1, 2. There, that's better. So here's that point, that point, that point, that point. Graph my skinny ellipse. See what the author did? Looks like the same thing. Is an ellipse. There's the 4 and there's the 9. So you did good. There's our picture. Now, I graphed it in rectangular, but what I'm going to do right now is I'm going to show you how we can graph it in parametric, because remember that graphing in the conic section was actually kind of difficult because we'd have to solve for y, remember? And y would be equal to 1 minus x squared over 4. All of that times 9. And then I got to take the square root of all that. So, and there's plus and minus. That's a lot to graph both of those. But with parametric, I can graph them. Well, I don't have to do it. I already showed you how to get in. Hit the mode, hit parametric, and make sure that go ahead and hit graph and see if your t's were enough. Go ahead and look at your x's. You know, the x went to 2 here and 3 up here. So -2 to 2 and -3 to 3 on your y's will help a lot. All right, I think I will go and graph. You graph yours, I graph mine. Don't graph it in rectangular because that's a lot of work. Solving that for y, then you got to type all that in. It's going to be a lot easier to type in the parametric. Okay, I'm back, and that's what I keyed in. Parametric. There's x and there's y in terms of the parameter t. Then I made sure my t went from 0 to 2 pi because I put it in radian mode. So you do have to make sure you put it in radian. If you put it in degrees, you'd have to go from 0 to 360. Okay, I would just say do the radians. It's so much easier. That's 2 pi. And I really didn't have to change my x and my y. It seemed to, what I had worked out, because here's the picture with my calculator. Try it. Let me know if you have trouble. It is a tricky bugger, but I still have faith in you. Parametric representations. When you convert rectangular into parametric, there are a lot of different possibilities you could do, and we're going to do a couple. He makes the point that there were infinitely many, and I'll show you why there are many. Given two parametric representations, okay, and this is rectangular, because there's no t's in it. There's no two. First of all, there's no two equations. Parametric always has to have two. They're in a pair of metrics. Okay. The easiest thing to do is just let x equals to t. That's the easiest thing to do. And then by plugging it in, and you get y will equal to t minus 2 squared plus 1. So this set will give you the exact picture that this is, which is just a parabola shifted to the right 2 and up 1. It's a parabola that goes something like that. Okay? Well, try this out. It should make the same picture in parametric mode. Now, you could be fancy. You could say, let x equals to t plus 2. I'm just picking that because if I plug this into here, I'm going to cancel that out. So that gives me y will equal to t plus 2 minus 2 squared plus 1. That gives you a t squared plus 1. So that's kind of cool that this set will give you the same picture. Different equations. You could get really complicated and let x equals to t squared just for fun. Plug that in, you get y equals to t squared minus 2 squared plus 1. And there's just so many. Whatever you decide to let x to be, x could be equal to t squared plus 2. Plug that in, I get then y equals to t squared plus 2 minus 2 squared plus 1. Y equals to t to the fourth plus 1. There's another set of parametric equations that will give you the same picture. Let's see what the author has. Let x equals t. That's the simplest. He did what I did, t plus 2. But then he did something even crazier than me. He said let x equals tangent of t plus 2. Wow. If you choose to do x is t, you get the same answer. Y equals t minus 2 squared plus 1. If you say x equals to t plus 2, you get y equals to x squared plus 1. If you say tangent of t plus 2, that gives you y equals tangent squared, because plus 2 minus 2 cancel out, plus 1. Hey, that's an identity. That's another identity. What's an identity for tangent? Tangent squared. Let me write that better. I get in a hurry. Isn't that secant squared, by the way? Tangent squared theta. No, tangent squared t, sorry. So tangent squared is equal to secant squared minus 1, so that could turn into y equals secant squared of t minus 1 plus 1. Y equals secant squared of t, I believe, is my identity. Probably your famous graph in terms of parametric is the cycloid. And a cycloid it's kind of cool. It's kind of like you take a wheel, and what if it has a certain radius, right? And you put a piece of paint, or you put paint on one part of that wheel, and as that wheel goes around, that paint dot is going to go around, and then it's going to get touching again. That goes around, that wheel goes around, that dot, you see it? And that's really what's happening here. This shape here is a cycloid. Okay, and the generic form is some number times a plus a sine of t. A sine of t is my x. The y is my a minus a cosine t. They're not the same. They're different. So he's given you, this might be an example. Even if you didn't know it, it doesn't really matter. I'm not going to test you on, do you know what the name of this is? And so if I plot the points for parametric, I'm going to plug in a 0 for t. Sine of 0 is 0. Then 0 minus 0 is still 0. Pi over 4 is that 45-degree angle. So in this case, you plug in the t, you're going to get pi over 4 minus sine of pi over 4, which is 1 over the square root of 2, or square root of 2 over 2. Now, that's a calculator. I want to know what the calculator number is. I don't know what it is in my head. Well, let's do the pi over 2. That's 90. Sine of 90 is 1. So this gives me pi over 2 minus 1. Again, what's the decimal? But you get the point here. You can use a table. Matter of fact, your calculator will give you the table of values as well. He chose to do one full circle, and I know why he did, is because he's thinking of that wheel going around 360 degrees or 2 pi. So in one rotation, we ought to be able to get one cycle of the cycloid. There they are in decimals. Wonderful, okay? And so plotting those points by hand, which I don't know if that's important enough, 0, 0, must be where that paint started. And 0.08 is very small, up to 0.3. So what I'm going to do is I'm going to count very small. I'm just going to go like that. And then 0.6, that's at least a half, up 1. Then it's a pi, which is a 3, point something up 2. So 1, 2, 3, up 2. If this was a 1, this would be a 2. So I'm up here. And then a 5.7, it's almost a 6. So that was 1, 2, 3. Didn't draw. My points, my pi didn't draw. That's 3. So now I'm going up to like 3, 4, 5, 6. About here. Up 1 again. And then 2 pi, finishing up the circle, 0. So there's my picture. And if you go to another 2 pi, and you go all the way to 4 pi, you'll get the more circle. If I go left to a negative 2 pi, you'll get that piece. But let's see what the calculator shows me. There it is. See that wheel moving in there? That's what it's going to give you. Cycloid, that's called a cycloid. So whenever you have nothing else to do, ask somebody, what's this a picture of? And you can feel free to say, wrong. It's a cycloid. Cycloid has these points here that are these jumps. I mean, they're like little sharp turns. Okay. He talks more about a cycloid. A cycloid, if you're a physics fan, if you knew the velocity when you threw a ball or shot a rocket and it has a trajectory, see that, recognize that trajectory? In physics, you may have seen this problem, maybe. The velocity times cosine of theta the velocity that you are shooting it with and the angle that you're making from the horizontal is a horizontal component of this velocity, of this ball being thrown. The velocity times sine of theta is your vertical component. So by definition, if you treat it as two parametric equations, you're separating both of those, the horizontal and the vertical motion. It's a parameter, each with t in it. The x is much easier. X of t is very easy. It's just the simple v cosine of theta times t. But look at the y. You got the v sine of theta t minus 16t squared plus h. H is the height you are off the ground. Your arm is when it's thrown. It's a little more complicated, but it's useful to look at it in terms of a horizontal component and a vertical component. Almost like vectors. Hello, it is like vectors. It is a vector. 3 golf balls are hit simultaneously into the air at 132 feet per second. Wow, there's 90 miles per hour. Might want to memorize that. Maybe not. That means you could figure out what 60 miles an hour is or 30 miles an hour is. Anyway, 3 different angles. They're all hit with the same initial velocity. Assuming the ground is level, determine graphically which ball travels the greatest distance. So we're assuming that the golf ball is on the floor, on the ground. So I'm going to have 3 equations here. X will equal to my initial velocity, 132, times cosine of theta, 30, times t, and the y is going to be 132 sine of 30, and I admit I've got to go back and look. T minus 16t squared plus h. The only thing that changes for each of these is the angle. That's it. Everything stays the same. Oh, the height. What was my height? Ground level 0, so I don't even need that. That was my formula though. Next one. X equals 132 cosine of 50 degrees t. Y equals 132 sine of 50 degrees t minus 16t squared. And so this is a separate set. The third set, x of 3 equals 132 cosine of 70 degrees t. Y equals 132 sine of 70 degrees t minus 16t. So there's your 3 sets. Knock yourself, well, they're at least they're easy. The 30 is easy to do. The 50 and the 70, I don't know what the cosine of 70 is. So you have to plug them in your calculator. But what do you think? Which one do you think is going to go farther? The one that has a smaller angle or the one that has the larger angle? You would have to graph them and find out. Let's jump to the rest of the story. Notice they all have the plus 0, plus 0, plus 0. And 30, 50, 70, 30, 50, 70, they're all 132. So it's a pretty easy equation to use. Very useful. Graph them in parametric. And what do we find out? That the first one, nope, the first one was not the farthest. The second one was the farthest. That would have been the 70. No, that would have been the 50. 50 degrees went farther. There comes a point where if the angle's too high, too steep, that it goes up, but it comes down too fast. Then if you are not angled enough, it it goes far, but it doesn't go as far because it didn't have any, it didn't have as much of the vertical component. Same problem, same thing. Okay. Not going to do another problem, but you get the idea. Jack launches a small rocket from a table that is 3.36 feet from the ground. The initial velocity is 64 feet and is launched at an angle of 30 degrees. So find the rectangular equation. That's different. We know what it is in parametric. Polarimetric was the velocity, which is 3 point, no, velocity was 64. 64 cosine of 30 degrees t, and y is 64 sine of 30 degrees t minus 16t squared. This time I have a height, 3.36 feet. So there is my parametric. This time all he wants to do is convert this into rectangular. Let's clean it up first because these are easy angles. What's a cosine of 30? That's the square root of 3 over 2. So x is really 64 times the square root of 3 over 2 t. That turns into 32 square root of 3 t because the 2 goes into 64. Over here, sine of 30 is a half. That becomes 64 times a half t minus 16t squared plus 33.6. That turns into 32t minus 16t squared plus 33.6. That looks very familiar to projectile motion. But usually we put the negative 16t squared first, then we put the plus 32t, which is my initial velocity. Then I have my initial height, 33.6. This looks very familiar to me. All right, but this is still too parametric. How do I get rid of the t? Take the simplest equation. I vote for solve this one for t. T is equal to x divided by 32 square roots of 3. You take this t parameter, you're eliminating the parameter, and I'm plugging it into this t, and I'm plugging it into this t. So my equation for y with only x's will be negative 16 times an x over 32 square root of 3 squared plus 32 times x over 32 square root of 3 plus 33.6. Clean that up. Y equals negative 16 x squared over, I don't know what 32 squared is. I'm just going to put squared times 3 plus, now this one, this was a 32 divided by a 32. That cancels out, leaving x over the square root of 3 plus 33.6. I'm almost tempted just to leave it. Well, I can clean it up a little bit and get rid of this negative 16. I can say that cancels out one of the 32's part of it. X squared over 16 times 32 times 3 plus x over square root of 3 plus 33.6. I'm going to leave it. It's not that important to me to get it to be perfect. If I really want it, I'll put decimals. I think 32 times 32. Oh, that's not a 16 times a 30. It's a 2 times a 32. Because 32 divided by 16 is 2. And there's still a 32 left. Okay, that looks probably better. Anyway, I'm going to run with it. Yeah. He solved it for t just like I did. Got it. Same thing here. And these look different because he rationalized the denominator, I mean, and he finished multiplying the denominator. I'm still going to take my answer. Example 8, determine the total flight time and the horizontal distance traveled. We already have an answer for y equals an equation. So we just got to figure out how long it took to hit the ground. Once it went up, it has to come back down. So for any quadratic equation, find out what time values that the y value is 0, because that's the ground. So we take this quadratic, set it equal to 0, and we solve it using a calculator or quadratic formula. Go ahead and pause it and see if you can solve it without my help or without the help of the notes. Did you get it yet? Quadratic formula. 2 possible answers for time. A negative time or at 2.1. Well, it's obvious you can't have negative time. So we're going to take the 2.1. That was a total time in the air. Now you have to plug this in to the original equation and find out how high it's going to go. So here we go. Remember what we had was x of t was 32 square roots of 3 times t. This is my horizontal position. We found out that time was 2.1. We plugged it into here, and that tells you your total distance. The rocket traveled about 116.4 feet. Now, we could have just graphed the parametric equation, and if you would have put both those equations in, you would see the picture form. Hit trace, and trace it till you get to where the y value is 0. And it'll tell you exactly what the t was, and it'll tell you exactly what the x is. Try it. If you don't try it, you won't know if you like it. And that's it for your last lesson. Guys, this class has been great with you, and I'm not going to bother you again this week. I'll put up the homework for this, a very short one. I'll put up a test review, and your test will be Friday. And I won't bother you unless you have questions for me. Then after that test on this weekend, I'll put up a review for the semester. And my plans for that is next Thursday. Please let me know, message me and remind if 30 is an issue. And I'm going to check the schedule of STC if they're going to require me to give it a different time. But right now, my guess is Thursday. All right, guys. Be there. RB squared.